Hello students, welcome back to Easy BTech channel and you are listening to the course of Signals and Systems. Okay, so we are in first chapter and we were discussing about classification of signals, and in this video we will be dealing with the periodic and aperiodic signals for discrete time case, and we will discuss about the next classification, which is deterministic and random signals. Okay, so first let us talk about periodic and aperiodic signals for discrete time case. Okay, so for a discrete time signal x of n, we say that it is periodic with period capital N if it satisfies the given condition. So what is that? X of n plus capital N should be equal to x of n. So but what is capital N? The least positive integer value. Okay, the least positive integer. So n should be integer. Compare this with continuous time case. There the capital T need not be integer. It should be a positive real number. But for dis discrete time case, we need capital N to be integer. It should be a positive integer. Okay, the least positive integer value of capital N for which this condition is satisfied, we call that N to be the fundamental period. So what is that? We can extend that to, we can see that just like we have seen for continuous time case, the periodic signal x of n with fundamental period capital N can be periodic with integer multiples of capital N. So what do I mean by that? So we can see that x of n plus capital 2n, this again turns out to be x of n, and similarly we can go on and we can say that x of n plus some integer multiple m times capital N is also x of n. So any integer multiple of capital N can be the period of the signal, but capital N is what? It is the fundamental period. Okay, so differentiate that between, you should know the difference between the fundamental period and the period of the signal. Okay, usually when we say period, it's actually the fundamental period of the given signal. Okay, yes, now we will take few examples. The first example is we are asked to find the period of this signal x1 of n, which is equal to minus 1 power n. Okay, so let us write down that. So we can write down what is the requirement. We need x1 of capital N to be equal to x1 of n. So we have to find out capital N such that this condition is satisfied. So let us substitute the values. So what is that we have to do? We have to replace small n with small n plus capital N. So what do we get? Minus 1 power n plus capital N should be equal to x1 of n, which is nothing but minus 1 power n, and then we will split this. What do you get? So minus 1 power n multiplied with minus 1 power capital N should be equal to minus 1 power n. So what should be the capital N here? N should be integer number one, and it should be a positive integer, and hence n equal to 0 is ruled out. So what is the least integer value of n for which this given condition is satisfied? So for that we need n to be equal to how much? 2. Why? If you replace n with the 2, you will get minus 1 whole square, which is 1, and hence you see that minus 1 power n would be equal to minus 1 power n. Okay, and is 4 capital N equal to 4 is also the period? Yes, so n equal to 4, n equal to 6, 8, and so on. All are the periods of this signal. But what is the fundamental period? Fundamental period is n equal to 2. Okay, so in that way, for first signal, which is a periodic signal, fundamental period is n equal to 2. Now let us look at the second one. So it is given that x2 of n equal to how much? Cos pi n by 3. So again, what is the requirement? We need x2 of n plus capital N should be equal to x2 of n. So what do I mean by that? What do we mean by that? Wherever there is n, replace with n plus capital N. So we get cos of 2 pi n by 3 plus we have replaced n with n plus capital N. So you get cos of 2 pi n by 3 plus cos of 2 pi n by capital 3. This should be equal to how much? Cos of 2 pi n by 3. So when is this possible here? So the left hand side should be equal to right hand side. So this is possible only if the second term on the left hand side is multiple of 2 pi, 2 pi or integer multiple of 2 pi. So when do we get 2 pi? This is possible only when n equal to 2, n equal to 3, sorry. So this implies, so I'll write down that. So this is possible, correct? So this is possible for n equal to 3. So and hence what do we say? We say that the fundamental period of the second signal is how much? 3. Okay, if you replace n with 3, so 3 will get cancelled. We get cos of 2 pi plus 2 pi n by 3, which is nothing but cos 2 pi n by 3. And hence what do we say? N equal to 3 is the fundamental period of the second signal. So we can say that second signal is periodic with period 6, 9 and so on, but fundamental period is 3. Okay, right. Next, let us take the third signal, which is x3 of n equal to cos 3 pi n by 5. So what is the need? So what is the requirement? We need x3 of n plus capital N should be equal to how much? X3 of n. So what should we do? The same rule, replace n with small n plus capital N. So this implies, what do we see? We see that cos of 3 pi n by 5 plus 3 pi capital N by 5 should be equal to cos of 3 pi n by 5. So when is this possible here? So the second term should be 2 pi or integer multiple of 2 pi. Note that capital N should always be an integer. Okay, so just in case, so what do? We replace the second term with 2 pi. So we get 3 pi n by 5 to be equal to 2 pi. So what happens? Pi will get cancelled. So we get n equal to 10 by 3. But what is this? This is not a positive integer, right? So that is a rational number, and hence 10 by 3 cannot be the period of the signal. So now what is that we have to do? Now we have to look for next integer multiple of 2 pi. Okay, now we have to make sure that second term should be integer multiple of 2 pi, and we want capital N to be integer. So when is that possible? Let us see. So we replace 3 pi n by capital 5 to be equal to, let us say, 6 pi. So will this right hand side definitely the integer multiple of 2 pi, no problem, but we can n be integer. Okay, so when is that possible? This is possible only if n equal to how much? 10. Correct. If n equal to 10, so sorry, this is not equal to, so n equal to 10, so definitely that is a positive integer. So what is the fundamental period of this second signal? That is nothing but n equal to capital 10 units. Okay, so note the difference. So for example, for a continuous time case, if I take x3 of t to be equal to cos of 3 pi t by 5. Okay, so for this capital T equal to 10 by 3, that is okay for us. Why? This fellow, we want the period to be positive real number. 10 by 3 is a real number. We can take that as the fundamental period. But for discrete time case, we want capital N to be what? We want capital N to be a positive integer, and hence that condition is ruled out. Okay, so we have to make sure that we will get capital N to be we want capital N to be integer. Okay, so we want capital N to be integer. That is one condition. Okay, so that is always the fundamental condition, and we want to make sure that the whatever the terms you get, secondary terms, they should be integer multiples of 2 pi. Okay, right. Next, let us take a bit complicated example. By looking at this, we may feel that this fellow is not a periodic signal, but we will check. So what is that we need? We need x4 of n plus capital N to be equal to x4 of n. Okay, so let us see what do we get. So we get cos of pi by 3. We will take it out. So we replace n with n plus capital N. So you get n square plus 2n capital N plus capital N square, and this fellow should be equal to cos of pi n square by 3. Okay, so if you expand this, we will write down cos of pi n square by 3 plus 2n capital N pi by 3 plus pi n square by 3. And we want this to be equal to cos of pi n square by 3. Okay, when is this possible? So only when the circled term, right? So this n circled term should be some integer multiple of 2 pi. So that should be what? Integer multiple, right? So that should be integer multiple of 2 pi. So when is that possible? Let us replace n with 3. So what will happen if you replace n with 3? So that fellow will become, so 2n pi plus 3 pi. So this is not multiple of 2 pi, correct? So we will get 2n pi plus 3 pi, right? If we replace n with 3, 3 will get cancelled. You will get 2n pi. If we replace n with 3, you will get a 9 by 3, which is 3 multiplied with pi is 3 pi. So this is not multiple of 2 pi. Okay, so this is not multiple of 2 pi. So that is ruled out. Now what is that we do? We replace n with 6. Let us check what happens if you replace n with 6. So if you replace n with 6, what will happen? You will get this term. So that term would be how much? 3 times 2, that should be 6n pi, correct? We replaced capital N with the 6, so we'll get 2 will get cancelled, you'll get 4n pi. Plus here what happens? We replaced n with 6, so that is 36 by 3, which is 12. So 12 times pi is 12 pi. So what happens here? We got the term, encircled term, to be 4n pi plus 12 pi. So that fellow can be written as what? So I can take 2 pi out. So you get 2n plus 6. So definitely this is integer multiple of 2 pi. Okay, so integer multiple of 2 pi, and hence what do we say? We say that the given signal is periodic with fundamental period n equal to 6. So by directly looking at the signal, you may feel that this fellow is not periodic, but if you try to solve from the first principles, you can see that the given signal is a periodic signal. So compare this with a discrete time, continuous time signal of the same form. So you get cos of pi t square by 3. So definitely this signal is not periodic. Okay, you can easily prove that this fellow is not a periodic signal, but cos pi n square by 3 is a periodic signal. It's a discrete time periodic signal with period n equal to 6. So in that way we have some differences between continuous time case and discrete time case. Okay, now let us take few more examples x phi of n, which is what is the requirement again? X phi of n plus capital N should be equal to x phi of n. So if you just replace n with n plus n, what do we get? You get e power j times n plus n should be equal to e power jn. So this implies what is the need? E power jn multiplied with e power j capital N should be equal to e power jn. So but you can easily see, and what is the need? What is the requirement? We want this fellow to be equal to 1. So if you want that fellow to be equal to 1, we need capital N to be integer, capital N to be what? Integer multiple of 2 pi. Okay, so capital N should be integer multiple of 2 pi. So if capital N is integer multiple of 2 pi, so definitely that is an irrational number. So this implies n is irrational. Because it is an irrational number, it cannot be integer, and hence what do we say? The given signal x phi of n equal to e power jn cannot be periodic. So this fellow is not periodic. Why? You cannot find any integer value of capital N for which the given condition is satisfied. Okay, and the same rule applies for this signal, but I will give this signal as homework. So you have to try whether this given signal x6 often is periodic or not. Okay, and you what should be the answer? You have to get the answer that it is not a periodic signal. Okay. Okay, so next let's talk about what happens if you take linear combination of discrete time periodic signals. Okay, so let us assume that x1 of n is a discrete time periodic signal with period n1, and let us say x2 of n is another signal which is periodic with period n2. Now question is what happens if you take linear combination of these two signals. So what do I mean by that? You amplitude scale x1 of n with a and you amplitude scale x2 of n with b and add them, then we call that as a linear combination. So if you take linear combination of these two signals, is the resulting signal periodic? That we will check. Okay, so let's assume that x3 of n is this new signal, which is a x1 of n plus b times x2 of n. Okay, so we know that x1 of n is periodic with period n1, and definitely it is periodic with period integer multiples of times n1 and so on. Okay, so we have already seen in continuous time case that if you want to have the linear combination of the periodic signals to be periodic, what is the requirement? We need the ratios of the periods to be rational numbers. Okay, so we want the ratios of the periods to be rational number. So definitely, so what is the rational number? A rational number is nothing but it is a ratio of integers. Okay, so definitely here for a discrete time case, we already know that the periods n1 and n2 are integers, so definitely their ratio definitely is a rational number, and hence what do we say? We say that ax1 of n plus bx2 of n is always periodic. For continuous time case, it's not the case. Why? Ax1 of t plus bx2 of t is periodic if and only if their ratios are rational. They can be irrational also, but here what is happening, because the periods n1 and n2 are always integers, the ratio is always a rational number. Because it is always a rational number, the linear combination of a discrete time periodic signals is always periodic. Okay, hence what do we say? Hence x3 of n is always periodic. Okay, hence x3 of n is always periodic. So that is the difference. For continuous time case, the ratios should be rational, but for discrete time case, because the ratios are always rational, the given linear combination is always periodic. Okay, right, and the period is given by LCM is, and the period is given by n equal to LCM of n1 and n2. Okay, LCM of n, same as we have seen for continuous time case. So period turns out to be the least common multiple of n1 and n2. Okay, right. So here we will take a few examples. So let us take the first signal to be 2 sine pi n by 3 minus cos of pi n by 4. We want to check whether this signal is periodic or not. So definitely the first signal, this is looking like ax1 of n. Instead of plus we have minus, so that's okay. We have, it is looking like ax1 of n plus b times x2 of n. So what is the period of the first signal? So that you can easily see that that is equal to 6. And what is the period of second signal? So that you can easily see that that is equal to 8. Okay, so period of the first signal is 6 and period of second signal is 8, and hence what do we say? Because if you take a ratio, it is 6 by 8, which is nothing but 3 by 4. That's always a rational number, and hence the period n is given by how much? LCM of 6 and 8. So that turns out to be how much? 24. You can prove that the LCM of 6 and 8 is how much? 24. Now instead, now let us go to the second example. So what is second example? That is nothing but it is similar to first example itself, except that we have replaced this minus sign with multiplication. So how is this looking? So this signal is looking like 2 sine A cos B, and hence what is that first thing we have to do? We have to split this. So we have to split, you have to write it as a linear combination. So this is looking like what? 2 sine A cos B, so which is nothing but sine of A plus B, which is sine pi n by 3 plus pi n by 4 plus sine of A minus B, so which is sine pi n by 6 minus pi n by pi n by 3 minus pi n by 4. So if you simplify that, so let me do that here. So what do you get? So first signal would be sine of 7 pi n by 12 if you take LCM and do that, and second signal would be sine of pi n by 12. Okay, and you can see that the first signal period n1 turns out to be 24, and even for the second signal n2 also turns out to be 24, and hence what is the period of this whole signal? N is nothing but LCM of 24 and 24, which is nothing but 24. In that way we can find the period of the product of sinusoidal signals also. So you take, for what is that you have to do? You have to split the signal, or you have to write the signal as a linear combination of sinusoidal signals. Okay, right. So let us go to the next topic, which is what happens if you take linear combination of multiple number of periodic signals. So what do I mean by that? We have x1 of n signal with period n1, we have x2 of n with period n2, and we have x, and so on up to we have m signal. So mth signal has a period nm. Now question is, what is the period of the linear combination of these signals? What is the need, or what is the requirement? We need all the ratios to be rational. Okay, so we need the ratio of all the periods. Okay, so we need ratio of periods to be rational. Okay, so to be rational, and you that is the case. Okay, that is the case. Why? Because the periods are always integers, the ratio definitely turns out to be rational. So this is the case. This indeed is the case, right? Okay, so this indeed is the case, and hence what do we say? Hence the given signal. What is that? Summation k equal to 1 to m ak xk of n is what? Is always periodic. That fellow is always periodic, and the period is given by how much? And the period is given by n is equal to LCM of all the periods, that is n1, n2, and so on up to nm. So that would be the period of the linear combination of all the signals. Okay, right. So how do you compare this with this continuous time case? Linear combination of a continuous time periodic signals need not be periodic. Why? If any one ratio turns out to be irrational, gone case. So that given signal is not periodic. But for discrete time case, the ratios of periods are always rational. Why? Because the periods are always integers, and hence the ratios is always rational number, and hence the linear combination of these signals is always periodic. Okay, so that is important, always periodic. Okay, right. So next we will take few examples here. So we are asked to find the period of these signals. So for this is again looking like a x1 of n plus bx2 of n plus cx3 of n. So definitely we have to find the period. For first signal we can see that period is 6, and for second signal we can see that period is 12, and for third signal we can see that period is 8, and hence if you take ratio of the periods, you pick up any two periods and take the ratio, that turns out to be a rational number, and hence we need not check whether they are rational or not. We have to find just the period of the signal, which is nothing but LCM of 6, 12, and 8. And if you want to do that, we can do it here. We take 6, 12, and 8. We take first 4, so that should be 6, 3, and 2. Next we'll take 3, that should be 2, 1, and 2, and finally we take 2, so that should be 1, 1, and 1. So what is the period? 4 3s are 12, 12 to the 24. So that turns out to be 24. So that would be the fundamental period of this signal. Okay, right. In a similar fashion, we can do it for this example also. But what is that I have done? I have taken the product of the signals. Okay, so what is the first step? So we should write this signal as linear combination of sinusoid. So first signal is okay, but second signal is not looking linear because there is multiplication. We want addition. So we should write minus j times. This is looking like 2 cos A sin B. So that is nothing but sine of A plus B, or we'll say sine of A minus B, sine pi n by 2 minus pi n by 3 minus sine of A plus B, which is nothing but sine pi n by 2 plus pi n by 3. Okay, so that simplifies to how much here? E power j pi n by 4 minus j times sine pi n by 6. So minus into minus is plus j sine, what do you get? 5 pi n by 6. Okay, and now this signal is looking like ax1 of n plus bx2 of n plus cx3 of n, and hence what do we say? So this signal is periodic, and what is that we have to find out? We have to find the period n1, n2 and n3. That I will leave it as homework. And finally we have to find LCM of n1, n2 and n3 to get the final period of the signal. So that I will leave it as homework because this is similar to the previous problem what we have seen. Okay, so finding the periods n1, n2, n3 is up to you, and taking the LCM will give you the final period n. Okay, so next let's move on to the next classification, which is deterministic and random signals. Okay, right. So we will compare and contrast these two guys. So what is a deterministic signal here? It is the physical description of that signal is completely unknown. So for example, temperature. Okay, so how for example, if you look at the temperature, we don't know what is the mathematical equation for temperature, right? So can you tell what is temperature tomorrow at 9 a.m.? It's not possible. So you can say that it is cool, but what exactly is the temperature? We don't know. So why? Because the temperature usually depends upon multiple factors whose physical phenomena we are not aware of, and hence we say that that is a random signal. Okay, and what is the deterministic signal? So deterministic signal is the one which we can say, or we can say that the physical description is completely known. Okay, and for random signal, physical description is not completely known. Okay, and what do we say about deterministic signal? It can be mathematically represented. For example, cos t, e power jt, all these are deterministic signals. Whatever signals we see in this course of signals and systems are all deterministic in nature. Okay, and when we talk about random signals, so we don't have a proper mathematical description of the signal, but we deal that with what is called random variables. We deal with the concept of random variables. Okay, right. So, and as I said, deterministic signal, we can define the value, or we will know the value of the signal at any instant of time. For example, y of or x of t equal to cos t. What is the value of x of t at t equal to maybe after 100 years? We can tell because we know the equation. We just substitute the value of t and we can get the value of the signal, but that is not the case for random signal. So as I said, temperature tomorrow at 9 a.m. we don't know. So temperature at tomorrow 2 p.m. we don't know because we don't have a proper mathematical description. So the concepts of the deterministic signals we see completely in this course of signals and systems, but the concepts of random signals we will deal with in the course of what? Random process, probability, random variables and random process. With that, I will stop this lecture. We will continue the remaining things in the next lecture. Thank you.